express what that quantity is. How do you measure that particular physical quantity? We are going to talk about momentum in today's class, what force is, and also describing all the three laws of Newton, that is Newton's laws of motion. The guiding light of this entire unit of mechanics. Then you would say that of course when you're applying the force, you're supporting the motion of the car, and hence hello students, welcome in today's class. So today's class is in continuation with what we have been doing so far related with forces. So if you remember, we have started with the unit where we are discussing the effects of force and its association with motion. So in the previous classes, if you remember, we have talked about what are Newton's laws, how they govern the motion of an object and all those things. And then we have also talked about the basics of or the various types of forces. Okay, so if you remember one thing here, that we had talked about two situations of forces. One is balanced forces and the other is unbalanced forces. So when it is an unbalanced force, you would say an object would move or would change its state of motion. But my question is, do you remember that when we talked about balanced forces, so for example, there is any object, let's say there's any object like this, and we apply balanced forces. Let's say we apply a force F here and another force F here. What happens then? So you said that you would say that there is no net force and there won't be any change in state of motion. So that's correct. That's correct. If you apply balanced forces, so I have this, if I apply balanced forces, if I apply equal forces and opposite forces on this, what do you expect? Will it change its state of motion? The answer is no. But then can some other thing happen? Let's find it out today. Okay, so that's what today's class is about. We are talking about the various other effects of forces. Okay, so one by one I will just brief you what we are going to do today. Forces acting on solids. So precisely we are going to discuss forces acting on solids, and that too majorly in context of springs. Okay, majorly in context of springs. And while we are doing that, so you can imagine when you apply a force on spring, it will either elongate or stretch, or it will compress depending on in which direction you apply the force. But when you're doing that, you're either applying balanced force like this, like you're pressing it, or you are elongating it. So the net force is zero. Spring is not going anywhere. It's just either compressing or stretching. That is what we have to discuss today. Okay, so there are some technical terms associated with it. The limits of proportionality, spring constant, Hooke's law, Robert Hooke. So Hooke's law, what is that? All that we are going to discuss. Very easy yet very important. Many graph related graphical questions also are framed in this category. Okay, but in general also you should understand the importance of springs. Okay, spring provide you that shock absorbing tendency, if you understand, like the suspension of your car and stuff like that. And it also provides the restoration tendency. It also provides the restoration tendency. So for example, you apply a force, you deform a you deform a body or do something like that, dislocate the body. If you want to get it back to the original position, that is also where the spring is going to come into play. Okay, so all these things are going to be very important for you. I think we shall start with today's class. Briefly you can write what we have done today, what we are going to do today. Briefly you can write that and then we will start. All right. Okay, so forces acting on solids. Okay, so first let's talk generally. So when you apply a force, you can stretch something. So can you imagine this is like a balanced force? Okay, you can bend something. Okay, this is also something you can understand. You can squash a bottle like that. Okay, or you can twist something. All these, whenever you're doing this, you are deforming the solid. You are changing its shape and size. That is what we are talking about. That a force can also cause a change in the size or the shape of an object. Okay, force can change the size and shape of an object. That is what we are going to talk about today. Okay. All right. So now let's understand this one. Springs. Springs are designed to stretch a long way when a small force is applied. So that is what springs give you. Maybe you cannot expect that with a string. You apply a force on a string, you don't expect it to stretch like that easily, unless it is made of that, that kind of a material like rubber where it can still stretch. But springs have that tendency. Even if it's a metallic spring like a copper spring or a steel spring, still we can, elongate it or compress it thanks to this shape that we have. Okay, so you can see this is like the natural length of the spring, where all the coils are in this format. When you now this is one easy way of applying force. You hang some weight from the spring. So when you hang a weight from the spring, you see that it's going to stretch. It's very obvious. What will happen if you increase this weight, you increase this force? So you put one more standard weight here. What do you think? What do you see here? What do you think is going to happen? So it is like the spring is going to elongate even more. Can you clearly see that? Okay. So what are we going to do here? So for that, there are two technical terms that you need to understand. First is the load. Okay. So when I was talking about this, we are applying a force. That is basically the load. Okay. That is basically the load. The load that you're applying on the spring, that is the force. So for example, if you remember, let's say this is 1 kilogram weight. This is 1 kilogram. So you do understand that the force of gravity on 1 kilogram is going to be 1 times g, that is approximately 10 Newton, like 9.8 but almost 10. Okay, similarly this is going to be, let's say, 20 Newton if we imagine each bar to be 1 kilogram. So what are we doing here? We are increasing the load. So now you understand load means the force basically. Okay, the force, usually weight, stretches an object of a spring. Okay, and it is therefore measured in Newton. If you remember, weight is measured in Newton. Okay, next is extension. So it's very obvious what extension is going to be. So this is like its natural length, let's say. Okay, hypothetically let's take it, let's say 10 centimeter for reference. Okay, so what is the natural length? Let's say 10 centimeter. Now you apply some force, you suspend some weight from the spring, and this length becomes, let's say, 12 centimeter. Okay, how much? 12. So what is the extension? The answer is going to be 2 centimeter. Now let's say you put one more weight and this length becomes 14 centimeter. So what is the extension? Is it 2 or 4? Answer is going to be 4. Why? Because extension is always taken as the change in length from the natural length. So extension, you can denote it by x, is always the length minus the natural length. Let's say the natural length is L naught. So this is going to be L minus L naught. So that is why it was 12 minus 10, that is 2, and then it is 14 minus 10, that is 4. Okay. So very easy, you do understand the increased length of an object. Okay, and majorly we are talking about spring. Okay, for whatever object is attached to the spring. Okay, so that's about the basic terminology, load and extension. So now before we even go to the next slide, can you anticipate how load and extension would be related? So you would clearly say that you increase the load and the extension obviously follows the same trend. The load increases, the extension increases. The load decreases, the extension will also decrease. So can you anticipate already what Robert Hooke verified? Can you expect that already, that on increasing the load, extension will also increase? Now understand, there are two things here. One thing, you can definitely call it proportionality. What can you call this? Proportionality. That extension is proportional to the load. More the load, more the extension. But now there is a term called direct proportionality. What is it? Direct proportionality. So direct proportionality means that if you increase the force by some factor, that is the load by some factor, the extension increases by the same factor. Understand? I will take an example. Let's say the first case, force is 10 Newton, extension is let's say 2 centimeter, alright, easy. Now the force becomes let's say 20 Newton, okay, the extension also becomes 4 centimeter. What do you see has happened? So you would say if the force has increased to twice, the extension has increased and also by the same factor. If I call this now let's say 30 Newton and extension again becomes 6 centimeter. So you have tripled the force now, the extension has also tripled. What does that mean? That it is directly proportional. On the contrary, let's take another example very quickly. Let's take another example. Let's say the force initially was 10 Newton and the extension was 2 centimeter, alright. Then the force became 20 Newton, extension also became 4 centimeter. So you have doubled the force, extension has also doubled. Now, let's say you made the force 30 Newton, but the extension now becomes 7 centimeter. How much does it become? 7 centimeter. So now, is it direct proportionality? Think about it. Force doubled, extension doubled, directly proportional. Force and extension are directly proportional. But if you have tripled the force, right? If you have tripled the force from 10 to 30, the extension has become 7 from 2. So this has become 3 times. Can you clearly see? But this has become 3.5 times. So has the extension increased by the same amount? Answer is no. Then you will not say that this is, following the direct proportionality. Okay, it is not following the direct proportionality in that sense. So if it is directly proportional, can you anticipate one thing very quickly here? That force and extension, the graph would be a straight line with a uniform gradient, but that is going to happen only if force and extension are directly proportional or the proportionality is followed. Then if the graph takes a curve like this, then we won't say that that proportionality is being maintained, and then we will say that we have achieved the limit of proportionality. What have we achieved? The limit of proportionality. And then it's not being directly proportional and it is increasing, extension is increasing with force, but it is not following the same factor, it is not following the exact same factor. Okay, so I think a lot of information here. Let's again revise what we have talked about. So we are talking about how springs would behave when they are subjected to a load, that is some weight is hanged and therefore a force is applied. And then we are talking about how they respond. So initially the response is very clear, that force increases, the extension increases, but if it is directly proportional, then we will call it Hooke's law. So that is what Hooke's law is. But I will wait here before we move on to the next one. You can copy down the important thing. This was just for reference, don't need to copy this down. Just write load. What is load? The force applied on the spring. And what is extension? The increased length, the increase in length. Okay, so the increased length of an object is a, okay, so this is increased length as in the increase in length, keep that in mind. So if it was like initially 10 and now it became 12, so extension is 12 minus 10, that is 2. All right, so next let's talk about Robert Hooke. So now I have already told you that force is going to be directly proportional to x till the limit of proportionality is there. So this law states that the extension of a spring is proportional to the load applied to it. So proportional here means directly proportional, provided the limit of proportionality is not exceeded. Okay, so till the direct proportionality is there, we call it as the limit of proportionality. Okay, now there has to be a constant of proportionality, and let's call that constant of proportionality as k. Okay, let's call that as k. So what is this k? This K is called the spring constant. What is this called? Spring constant. Okay. So why? Because different springs will have different tendency to stretch or elongate. Some springs might easily do that, while some might be made up of a rigid material or maybe their thickness, which won't allow them to stretch that easily. So not all springs will give the same behavior. So for example, if I have two different springs, let's say this one and this one, it doesn't have to be the same extension on applying the same force. If I apply 10 Newton on this and if I apply 10 Newton on this, you don't have to expect the same extension in both of them. So there is this constant of proportionality which will decide that how easily, you know, this is going to happen. In fact, you can call it vice versa, how difficult it is. Why? Can you understand? Because if I rewrite this expression, this is x is equals to f by k. What is this? X is equals to f by k. So more the value of k means lesser extension it will exhibit. So can we call it as the stiffness constant also? Yes. So sometimes it is called spring constant, sometimes it is also called stiffness constant. So if I tell you that this one extended by 1 centimeter while this one extended by 3 centimeter, then what do you think? Which spring is easily extending or deforming? Answer is this one, the second one. So it will have a lower value of k. The first one is extending less, so it is more rigid, it is more stiff, so its stiffness constant will be more. Okay, so it depends on the nature of material that you have used and all those things, but I don't want to discuss those technical things over here. You can still understand that not all springs will have similar behavior. So this law is clear, I hope, that what Hooke's law is all about, and secondly this F is equals to Kx. So we will use this very often, but this is only valid till limit of proportionality, that is, it is directly proportional. The force and extension are directly proportional. Till that point we call it as the limit of proportionality, and then they start showing more extension even for lesser force. So then the graph does not follow the straight line pattern, as I have just discussed, that you know this graph might then curve a little. So when it curves, it actually, you know, means that the proportionality is not there. One thing that I wish to discuss, let's draw these two graphs now, for the first spring, let's say, and for the second spring. How do the two graphs differ from each other? So the first one, you know, it's showing lesser extension. So the graph should be a straight line, but somewhat like this. But on the contrary, the second one is easily showing extension. Okay, so let me draw again. So this one is showing lesser deformation or lesser extension, the first one. Second one is showing more extension. So it should be like this. Can you compare? The first one is showing lesser extension for the same force, while the second one is showing more extension. So when you have applied a force of 10 Newton, this has shown an extension of 1 centimeter, while this has shown an extension of 3 centimeters. So what do you understand? That, you know, if the spring is stiffer, this is steeper. If the spring is easily extending, then this graph is less steep. Or can we say the gradient of this graph? The gradient of this graph, if you understand, gradient is change in y over change in x, or the rise over run. That gradient is nothing but f by x, that is k. So that is why the first spring has more stiffness constant, so it is having a higher value of gradient. The second one is a lower gradient. So I will explain this again to you. This is about Hooke's law, F is equals to Kx, this graph, and K depends on the type of spring. Okay, but for a given spring, K is same. Okay, keep that in mind. Copy down the important things, then we move forward. All right. Next thing is about this only, that less extension per unit force. so high spring constant. So whoever is going to show lesser extension, so now I am just comparing two different springs like this. Okay, so this spring, what do you think is going to happen? High spring constant, it's going to be difficult to extend this one. The turns are very tightly bound, it feels like that. Here it is a slinky kind of a spring which can easily. So now can you compare it in that context? This will have a higher value of K while this will have a lower value of K. Okay, so K is equals to F by X. One more thing I wish to discuss here, that is the unit. So unit is normally Newton per meter. Okay, if you talk about the SI unit, but very often you don't expect, you know, an extension of meters. So sometimes, and in fact many times, the value of K is given in terms of Newton per centimeter. It is given in terms of, so for I will right away take an example. Let's say if I tell you that, you know, the stiffness constant is 20 Newton per centimeter. So what do you think it is? For every 20 Newton force, the extension increases by 1 centimeter. So if I ask you that if a force of 80 Newton is applied, okay, what is going to be the extension? What is going to be the extension? So you would say that for every 20 Newton the extension is 1 centimeter. So for 80 Newton the extension should be 4 centimeter. But still let's do it. F is equals to Kx. K is like 20. So keep in mind the unit. If it is like Newton per centimeter, then the extension that will, you know, come as an answer is also going to be in centimeter. So now force is how much? Force is 80. So 80 is equals to 20x. Value of x is 4. But keep in mind it is not going to be meter. It is going to be centimeter, because the unit here of K is Newton per centimeter. If it would have been meter, then extension would also be in meter. But this is the extension, not the final length. It is the difference in the natural length and the final length. That is what we call as the extension. Okay. Alright, I think the basics you do know. Still write K equals to F by X, and you can write this example very quickly and we move forward. Alright, now let's start with the numericals. Let's take a couple of numericals. We've understood how springs behave. One more thing, the major application that you can think about of spring is spring balances, that you use this to measure the weight of things as well. Okay, so spring balances also function, or their, you know, mechanism is based on springs that, you know, you already know how much a spring will extend for a particular force. You use those facts to measure weight of unknown objects. So just for an idea, spring balances obviously work on Hooke's law as well. Okay, the table below shows 3 columns to record the result of an experiment to stretch a spring. Draw a load versus extension graph to see how extension depends on the load. So one column is for the load, second column is the length of the spring, and the third column is the extension. Keep in mind, extension. Okay, so let's first fill in this extension thing. Very quickly, let's do it. So first case extension is 0 because there is no load. That means there is no extension. In fact, that means 15 centimeter is the natural length of the spring. Now the extension becomes how much? The length becomes 17.5. So the extension is 2.5 because 15 has become 17.5. So the extension is 2.5. Now 15 has become 20. So the extension is 5. Similarly 7.5, similarly 10. Now 35 minus 15 is going to be 20, and 45 minus 15 is going to be 30. Okay, so we have to draw the graph. To draw the graph, let's decide on a scale first. Y-axis we have to represent the force in Newton. Since we have 1, 2, 3, 4, 5, 6 and we have a scope of 12 blocks here, let's, you know, call on the y-axis 1 centimeter is equal to 0.5 Newton. So I am deciding on the scale here that, you know, every block means 0.5 Newton. So every 2 block will make 1 Newton. Keep that in mind. That's on the y-axis. On the x-axis, we have to go up to 30, and we are in, you know, skip counting in 2.5 in a way. So for x, let's do that only. every 1 centimeter on this, like this is 1 centimeter standard graph, means 2.5 centimeter. So let's quickly get the points. First is 0, load 0, extension 0. So this is the y-axis, this is the x-axis. Keep in mind, this is the y-axis, this is the x-axis. This is not needed here. Okay. So now the load becomes 1. All right, very quickly. So I think this point, because every 2 blocks is 1, and this becomes 2.5. So this, okay, 1 Newton, 2.5 centimeter. I'm a little short of space. So, okay, then 2 Newton becomes 5. So this is 2, this becomes 5, 2 Newton. Then 3 Newton becomes 7.5. 4 Newton becomes 10. So clearly you can see that it is going to be a straight line graph till here. Okay. So Hooke's law is being obeyed. Yes, 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 yes. Any which way you can straight away see, when you double the force, extension doubles. When you triple the force, extension triples. When you make the force 4 times, the extension also becomes 4 times. So Hooke's law is being obeyed. But look at this now. When the extension becomes 5 times, sorry, when the load becomes 5 times, the extension should also become 5 times. So 2.5, 5 times of that is going to be 15, but this is becoming 20. So it is beyond that. So it is not obeying Hooke's law, it is not obeying the proportionality here. So let's label that as well. Let's locate these points as well. So 5 Newton, okay, 5 Newton is here. The extension becomes how much? 20. Okay, 20. So every 4 blocks, 1, 2, 3, 4, 5, 6, 7, 8, somewhat here. Okay, here. So this is like 20 centimeter. Similarly, more 4 blocks will make it 30. 1, 2, 3, 4. So this is like 30 centimeter, and then the force is like 6 Newton. Okay, 6 Newton is here. So it is going to be somewhat here. Okay, so initially let's try to draw a straight line. Let's see if we would be able to do it. Okay, let's try to draw a straight line here, passing through all these points, almost a straight line here very easily. But then you won't be able to draw this as a part of the same line. Okay, so what you can see is that the proportionality is not there anymore. So initially Hooke's law is being obeyed. This is how springs function. I hope you were able to understand through this whole example. Let's take one more question and end today's class. I will wait. You pause the video and take a screenshot, and then we move forward. Okay. So the last question for today. So I've done the basics of springs today. 2 girls want to weigh a watermelon, but they do not have a kitchen scale. So they use a spring and a 0.5 kg bag of sugar to measure. Okay, so that's a very unique idea. They have a spring, they first standardize it, as I was saying, that how we can use springs to measure force. When suspended, the bag of sugar stretches the spring by 25 millimeter. Okay, so they have given us, when force is 0.5 kilogram, the extension is 2.5 centimeter. So what I have done is I have converted millimeter to centimeter by dividing it by 10. Okay, so we'll first use F is equals to kx. F is like so the value of G has to be taken as 10. Okay, so for simplicity I have taken it as 10. So this is going to be 0.5 kilogram. The force will be 0.5 times G. Okay, because we are taking 1 kilogram is equivalent to 10 Newton. So 0.5 kilogram is equivalent to 5 Newton. Okay, so 5 is equals to K and X is like 2.5. So the value of K is turning out to be 2 Newton per centimeter. So for every centimeter, that means there is a force of 2 Newton. Okay, let's start with the problem now. Now the watermelon stretches it by 3.75 centimeter. Then we have to calculate the spring constant. Okay, that is already done. Spring constant we have already calculated. Calculate the weight of the watermelon. Now we will again apply for the B part. F is equals to kx, and the value of f is what we have to find out. But thankfully the value of k is still the same, 2 Newton for every centimeter. So I will put the value of x as 3.75. Do you understand why 3.75? Because millimeter is converted into centimeter by me by dividing it by 10. Okay, so this value of force turns out to be 7.5 Newton. So what is the weight of the watermelon? The answer is 7.5. But if you want to know its mass, then do remember that you equate force to mg, and this value is given to be 7.5. So m is going to be 0.75 kilogram, or it is going to be 750 gram in 3SF. Okay, keep that in mind, that the value of force is something else and mass is something else. Don't take weight as mass. Weight is the force. If you want to give the mass, then you have to talk about F is equals to mg. But let's not go there and focus on that part. But I hope you've understood how springs are working, and we will majorly deal with numericals where the Hooke's law is being obeyed. Okay, but that's all for this particular class. That's all for about springs that we need to know, and the graph part and everything I hope you were able to understand. In the next class we will talk about moments of forces, one more effect of force that we are going to discuss, and then I think we will also very soon start with the previous year questions, which is going to be very exciting because we already know the previous chapters now. So a lot of questions which involve multiple concepts of forces and motion, we should be able to do them. So a lot coming up in the upcoming videos, but that's all for this one. See you in the next one. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.